And here's one, if for all x not p of x, does that imply not for all x p of x? They, classically all those things are the same, but constructively, you can ponder that for a little while. Because remember, the exercise Bob gave was to show that not p or not p, so I don't know. In some cases, well, anyway, this one is true. Well, I guess we're just going to have to live with that flickering thing. It's very annoying.
I have one thing I should show you.
Okay. Change the refresh rate. Or you're looking
See
at.
if it works for Ubuntu. So
This is a.
R
so-
and R.
Okay,
Go
so-
to shell window.
X R.
And R. And so that should give you
Okay.
the available rates that you have.
Whoa. And then.
So it looks like you have 60. Oh, it's weird. You could try some of these. Those are like 60.3. I wonder if that's
Where do you see 60.3? Like, oh, right there.
there. So you can just do XR and R dash R and then pick a different refresh rate and see if that works. There's also 59.9. Maybe there's just something that's like slightly off.
X render.
Or actually, it looks like there's two.
What do you think the stars mean?
I think the star is like the one that's being used.
Oh,
Maybe it's using like 59.9.
And it should
maybe
use
you need
60.
60 or something like that. So try dash R 60. See if that works.
Discrepancy between the resolution on the screen here and there. So if you just, I would try this.
So that doesn't seem to help.
Still
So,
flashing.
Yeah.
so go back to the display.
Okay.
Well, you can change the resolution as well.
Yeah.
with
Here?
this. Yeah.
That's one way to do it.
Yeah,
You
well,
can also do it
yeah.
from
Oh, you can do it from the
settings.
display?
Yeah.
Okay, maybe it's easier
Yeah.
from there.
Okay, displays.
Displays. And
Now,
try
try setting one of the other
Trying
ones.
it down to a lower resolution or something like, try the
Yeah.
Those are
800 by
those are the only.
Try this one.
Yeah. 'Cause then, if I do that with my giant font, it's going to be
Oh,
huge.
that's
but
fine, but
yeah.
you can fix that later.
I can.
So,
Well, not so easy, because the font that NewPro uses is like.
Doesn't like that.
It looks very fuzzy, doesn't it? No, still flashing.
All right.
All right.
I guess nothing seems to be working.
So I think it, could it, this
I
is,
wonder if there's like
so I just wanted to show you some more things in NewPerl, and we're going to highlight some facts. I'm going to show you a bunch of more types that we have in NewPerl and what we do with them, and also some facts about that computation relation. I think so. This was Howe's wiggle relation. So this is this computational bisimulation, and it says T1 is squiggle equal to T2 if T1 is what we call squiggle less than or equal to T2, and T2 is squiggle less than or equal to T1. And the definition of this, roughly, is for any canonical form theta, like pair, inl, is in, any canonical term that's, that's reduced now to a value. If T1 computes in any number of steps to theta of some A1 to AN, then there exists B1 to Bn such that T2 will compute to the theta of B1 to Bn, and A1 is squiggle less than or equal to B1, and AN is squiggle less than Bn. So this is a co-recursively defined relation. It says they're in the relation if, for any canonical thing, this, and then co-recursively the subterms are in the same relation. So it's actually it's a greatest fixed point of a certain relation. So it has the property that I think Amal was talking about using logical relations to prove that certain things were contextual congruences or contextual. So Howe proves that this relation is a contextual congruence relation in any computation system that satisfies a few basic constraints, which Nuperl does. So anyway, that means if the upshot of that is if I want to prove that G of T1 is less than or equal to G of T2, if T1 is less than or equal, if you've established this, then in any context it still holds. So that's a very nice property, and then that carries over for squiggle equal as well. So I want to show you how using that we can actually show. So here Bob gave you as this exercise to show that not P or not P. But how about P or not P by itself? We say, well, in constructive logic that's not a rule, but maybe it's still consistent with our system. And in Koch, they claim at least that the impredicative universe you can assume P or not P as an axiom if you want to. But in Nuperl, that's not the case. We can actually refute P or not P. And I'm going to show you how we actually can refute P or not P. In Nuperl is actually inconsistent with classical logic. So I'm going to show you a refutation of P or not P. Not for an individual P, but I'll show you. So I'm going to create. I have it here, but I'm going to start from scratch and show you. Refute, and I'm going to use properties of this computational. Refute the excluded middle. Okay. All right. So we're going to live with this flickering thing, and all right. So for all types T, and for all P that are propositions about T, so we use this symbol prop. It's just an alias for type. In Koch, prop means the impredicative universe, but in Nuperl, prop is just a synonym for type. All x in T or, okay, I'll just say, I can use, it looks nicer if I use this second order apply. Oops. What did I do wrong there? SO. What's happening here? Okay, never mind, I won't use that. App P of x not app P of x. Oops. App P x. So this is saying. Is this what I want to say? Yeah, I think this is what I want to say. So this is saying this is the excluded middle. Now I'm going to make a negation of that. Yeah.
Is there a reason to work with a set instead of just a combination? In other words, why don't you take P from
Yeah, you're right. That's what I meant to do. I forgot what I was going to do, so I'm going to just, yeah, okay. So we're just going to say, all right, yeah, that's right. Or P, not P, and we're just going to have this quantified over all propositions. P, and now I'm going to get rid of this. Control X, KP. Okay. So there's the law of excluded middle, so I'm going to put a not on that and claim that we're going to actually prove the negation of that. All right. So the first step, D0, then A auto. All right. Assuming the law of the excluded middle, for all propositions, I have to prove false. So here's what I'm going to do. I'm going to assert that given that, the following thing would be true. For all terms in my type base, either that term will have a value or it won't have a value. That's an instance of the law of excluded middle. So I'll have to show you what has value means, but either the term has a value or it doesn't have a value. Okay. So now I'm going to say auto here, and since that was just an instance of my hypothesis, it figured that out. Okay, so now I'm going to actually thin out hypothesis 1 because I don't need the general law of excluded middle anymore. Just this proposition right here that any term in base we can decide whether it halts or not is already inconsistent. Okay, so first let me show you what this has value thing is defined as. So this will look a little mysterious, but so eval is a call by value operator. So A has a value if when you do call by value on it to evaluate it, so eval A, so there's a choice of bound variable that's kind of bad there. It's basically saying this could just be let x. It's saying normally we'd say in ML you'd just say let x be A in something, but ML is an eager language. So to make the distinction between the lazy and the call by value we use the word eval if we're doing the call by value and just let if we're doing the lazy thing. So eval x equals A evaluates x and then returns. It would normally plug x into some context, but in this case we're just saying all we're trying to do is evaluate A and then we're going to return 0. And if we can't evaluate A, if it would run forever, then that side would actually diverge, and so it wouldn't satisfy this. This is the less than there is this computational approximation thing. So if 0 approximates that, then A must have had a value. So that's a way we can say, using just that as a proposition, we can say that something has a value. Okay. So now let's assert a few basic facts. Not bottom, not has value bottom. Okay. So what's bottom? Oh, bottom is primitive. Well, I guess we have various versions. Bottom could be just defined as the fixed point of the identity function. It doesn't really matter. Any term that just diverges. But I guess in our current system, we've put this particular concept in as a primitive. So anyway, bottom. So that means there's a rule to the effect that bottom does not have a value. So if I say auto, it should figure that out. Okay. So bottom is one term. It's in base. And it doesn't have a value. And let's assert that has value zero, for instance, does have a value. Okay, that's obvious. You do call by value on 0, you're going to, anyway. All right, now here I'm going to assert one more thing that I'm going to need. Yeah.
When I typed in that total,
Uh-huh.
it's, and I put auto, we zero has value, it says error, step, direct, not line.
So, right, you said assert 0 has a value. I don't know. Just try it again. Something. Yeah. All right, now I'm going to assert that it's not the case. And now I'm going to use so that less than or equal operator is what we call the SQ, the squiggle LE operator. So it's not the case that 0 is less than or equal to bottom. Because remember, this would say, for any canonical form that 0 computes to, namely 0, bottom would also have to compute to that, and bottom does not compute to 0, so that should be obvious, but do we have enough rules in the system to prove that? Can auto prove it? I don't think so. Oh, okay, it can. All right. But here I'll show you another proof. Just, I think it's never clear exactly why auto is getting things, because auto, it uses various primitive tactics, but it also just kind of uses lemmas in the library. And so if somebody had happened to prove that fact, auto would find it and just use it. So you're never quite sure. Is it really smart, or did it just happen to find that in the library? But anyway, if 0 were less than or equal to bottom, then I could assert that 0, or that, say, bottom, would be squiggle equal to 0. Because to do that, I use SQ equal, SQ equal, SQLE. That says you have to prove, by definition of SQ equal, you have to prove the two things. Bottom is less than anything. That's basically a primitive fact. Anyway, and then 0 less than bottom is what we have by our assumption. So anyway, one way or the other, we see that, let's see, am I done? Is this part? No, I'm not done. Oh yeah, sorry. Now I have bottom squiggle equal to 0. Now I can, because of this context property, I can use that squiggle equal to substitute bottom for 0 in any context. So like, for instance, I'll substitute it hype subst. If I hit this, it'll say, it has a Boolean to say, do you want to substitute forward or backward? Anyway, I'm going to substitute hypothesis 5 that bottom is equal to 0. I'm going to substitute that into, it doesn't really matter, say hypothesis 2. So now I have 0 has a value and 0 doesn't have a value. So now auto will see, okay, there's a contradiction. Anyway, so that's kind of a trivial. So now we have these three facts here. Bottom doesn't have a value, 0 does have a value, and therefore 0 is not less than or equal to bottom. So using those things, I'm now going to refute hypothesis 1. So the way I'm going to do it is I'm going to give hypothesis 1 a better name, rename variable in hypothesis 1. I'm going to rename it like Bob did, magic. Rename var magic in hypothesis 1. Is that right? No, it goes the other way. 1 magic. Rename. Oh, I didn't. This isn't the syntax for a variable. Variable has that kind of a quote. So now it goes this way. All right. So there we have magic is this operator that, given any term in base, it can decide whether it has a value or not. So we're going to use the standard proof that the halting problem is undecidable here, but it's phrased in terms of our computation thing. So I'm now going to assert SQLE, so come on, SQLE. I'm going to assert that something applied to bottom is less than or equal to that same something applied to 0. So no matter what I put in, if I put the same thing into those two term slots, that's going to be true by that context property for squiggle less than or equal. Since bottom is less than 0, it's in any context we're going to have that. So I have to pick the right thing that I'm going to use. I'm going to apply magic in some way to both sides of bottom and 0, and I'm going to get a contradiction. So here's what it is. Lambda t, we're going to say decide. This is the decide operator now. So magic applied to this t is going to be either inal of the fact that t does have a value, or inar of the fact that it doesn't have a value. So I'm going to decide which case does magic say for t. So I'm going to apply magic to t. If I get inal, then I know that t has a value. So the trick is to now put bottom there. Why do I keep mistyping that? And if I get an inar, then I'm going to pick 0. So this operator that tests whether t has a value and then does the opposite is the standard trick. Okay, I'm going to assert that, and I'm just going to use my SQLE. Whoops, I keep mistyping everything today. It's SQLECD. Okay, that just checked that context property and reduced it to bottom less than 0, which it got. So, okay. All right, so now we have that. And now we can sort of see why it's already in a contradiction, because, we'll just say reduce in -1, in hypothesis 1, -1, which is 5. It says, if, well, magic of bottom better say, since bottom diverges, magic of bottom better return the in our case there. And so we're going to get 0. And over here it says if this has gone off the screen for me. Over here we have magic of 0. 0 does have a value. So that better be the in L case, in which case we're going to have bottom. So this whole thing is going to reduce to 0 is less than or equal to bottom, which we already know is false. So we're almost done with this proof. So the way I have to do it is, this is the way I would do it. Move to concal -1. So this is what in Coq would be revert that hypothesis, push it back down here. Now I'm going to do, I guess Adam would say something like destruct of something. Anyway, well, I call it generalize a term in the conclusion. So I'm going to generalize this magic of bottom term. Whoops. Okay, so that says, well, by the type of magic, magic of bottom is either bottom has a value or bottom doesn't have a value. So we're going to now destruct using D on, we can say D5, or we can say D variable V, however we want to. Now we have two cases. Bottom has a value. Well, we already know that bottom doesn't have a value, so I can even say trivial. And over here, bottom doesn't have a value, but now I can say reduce. Just does the computation. Okay, so now we've got that, and now I do the same thing for the magic of 0. Gen concal term. What's that? Oh, okay. App 0. Oops, that's not a 0. Then a auto. All right, and then we do the same thing. D var V. Then reduce 0. All right, so now we've got that. Hey, I don't know why. I guess the reduce. Anyway, how about this? then try trivial. Oh yeah. Oh, I see. I remember. I didn't fold. Something arrows false is the same thing as not. I meant to do that earlier on. Fold. Hey. Oh, I typed the wrong kind of token. Okay. So now reduce. That's just doing the computation. Case inl returns the inl case. So now we have that, and now that's by hypothesis. So I can say trivial or hypothesis. Okay, now we're done. So we have now proved that it's not the case in new Perl that for all p, p are not p. We've actually refuted the excluded middle. So it's not, it's not the case that excluded middle is not, available in new Perl. It's just false in new Perl. So we have to step back and say, why is this? What's going on here? So Bob might show you in his talk, his original proof of this using this type that he called the. At the time, they called them the bar types, but we've now. And I'm going to show you the bar type in a second in another use, but. So the main thing is, that bottom. The fact that bottom is allowed at all in our system. Our system does not have strong normalization. Not every term in the system has a value. We have partial things. So the fact that bottom is there at all is part of the reason, and the fact that we can use, we have this type base. As long as you have some types that include this diverging thing, then you can do this kind of reasoning using type theory. So in Bob's original way of doing this, he took a type T and then he extended it. He put a bar over it, and that would stand for the type of values which either diverge or were in type T. But we don't really need to do that in this case because we already have a type like that. Base already includes things which diverge and things which don't diverge. So just using base was enough in this particular proof. And this particular proof that I just did was actually discovered by Abhishek Anand, as he was just investigating, all the consequences of this computational approximation relation. He was kind of just investigating to what extent new Perl already has kind of a computational version of domain theory built into it. This less than relation is similar to concepts from domain theory. And it kind of gives us, as far as I can tell, the power of proving most things that people would use domain theory to prove. I'm not sure of that, but for the most part it does. So I don't know. Does that explain anything so far, or do you think we should say more about what's going on there? Okay, so I think, yeah. How does top bar differ from base? So let's see. In top, the t-bar. Oh yeah, if this were the type top, this could be anything. Like you could have, int bar would be the type of things that either can compute to an int or have bottom. Yeah, but if we put so if we put base bar, then I don't think I can prove that base bar is actually the same thing as base, but maybe I can. I know I can actually prove this. I think. Yeah, I don't know. But essentially, I'm just saying. I could have used the bar type in this argument, but there wasn't any need to introduce it yet, because base by itself already has bottom in it, and the equality in base is squiggle equality, which is all we used in this argument. Yeah. Yeah.
You must have some restriction on those types which you can use for logic, as it were.
Yeah, so many times you want to know that a type only has values in it. so that you can say, for this kind of a type, I can always safely do a call by value and so on. So we do have the concept value type T, which basically just says every member of T has a value, and then we have a whole lot of lemmas that say if A is a value type and B is a value type, then A cross B is a value type, and so on. So basically, if you need this, basically you can just, like if you want to know you've done a call by value on something, and you want to know that that is actually going to return a value, you just sort of say auto, and it says, well, it infers a type for it, and then it uses these value type lemmas and says, oh yeah, that's right, it's a number or it's a product of numbers or whatever. So yeah, so we do have that, and it works fine. So yeah. So here's an interesting thing. In this function type, this is what we call the dependent function type, and in Coq they call it the pi type. But if f is a member of this type, then what form does f have to compute to? You might say, well, it's a function, so it has to compute to some lambda. F has to compute to a lambda. And we used to have that as a primitive part of the definition of the function type, but we've loosened that up lately because we said, really, we should be doing pure, our types, for the most part, we want them to just to be defined by the observations that you can make. So the only way to observe this f is to apply it to something. And so whether or not f is in here should just be defined by how apply works on f. So this should mean that f should be in here if for every a and a, if you apply f to a, you get something in b of a. And that's right. So in particular, if a is void, this is vacuously true. If there are no members of a, then this would be vacuously true. So that would mean that f would be in there no matter what. So that would mean that 0 is a member of void arrows int or something, or void arrows bool or anything. If the domain is empty, then there's no restriction. So not everything in a function type necessarily needs to be a lambda if you have the void over there. And now, if this b of a, so assume that a is not empty, then there is an a. But still, if this b could contain bottom, then still, like suppose there's an a and a for which bottom is a member of b of a. Then still 0 applied to a. 0 applied to a is kind of a nonsensical thing. You can't apply it, so it's stuck. It doesn't do anything, and so therefore it doesn't compute to any canonical form. So therefore it's squiggle equal to bottom, and if bottom is in this type, then that's allowed. So the only time you know for sure that something in a function type has to be a lambda is if for some member of the domain A, the codomain doesn't contain bottom. So again, just to do normal reasoning about things, you need to be able to rule out bottom being in certain types easily, but we can do that. So it's okay now. Okay, so here were two little puzzles for you to chew on based on what Bob said. So does anybody have an idea if any of these are true? This one says if there exists an x for which not p, then not there exists an x for which p. All these things are. What do you think? Yeah, you're right. The second one is now false based on what we just proved, because if this were true, since Bob had you prove this yesterday, if we just take if we just take T to be propositions, then we already know that it is the case that for all x that are propositions, not P or not P, because that's the exercise Bob gave you. So if this would imply this, then we would have not for all P that are propositions, P or not P. And we just proved that this is false. So not a false is still false. So yeah, so this one here, this bottom one, is called the general double negation shift. And some instances of it are true, but not all. So as we just saw, INNUPERL refutes this general double negation shift property. This one here actually is true. You can do that one as an exercise. But this is true, but not this one. So, all right. So now I'm going to show you some other. Any other questions about this particular thing? Okay. So what I wanted to show you now was the way we. Let's see. What am I going to show you? Let's see. I guess I'm going to show you. I'm just gonna pop up here. This is a little window called the top loop where you can just evaluate things like, you can just evaluate ML expressions and things in here. But another thing I can do is just use it as a scratch buffer to put things in. So list, the type of lists. So in Coq, that's an inductive type, as is everything in Coq pretty much, except for the function type. Inductive type. And that's a sensible way to do things. But in NUPERL, we used to have a version of an inductive type that was even more powerful than Coq's inductive construction. It was called the Mendler recursive type. And it's a very powerful fixed point operator, but at the moment, we don't know whether Nax-Mendler's original argument for the soundness of that actually holds in NUPERL anymore. So we decided not to rely on that anymore. So I'll show you the current definition of lists. So, oops, why did that not pop up? Right. Okay. So there is the current definition of lists, which might seem rather odd. So I said the type of lists are the type of elements of the colist type for which the colength has a value. So I'm going to show you what all those things mean. So list is meant to be a recursive type, but actually the co-recursive type is actually easier to construct. So we construct that first, and I'll show you how we do that. With these. Okay, so here's the definition of the colist. So the colist is the co-recursive. I'll show you what that is, but that's the corec forms the greatest fixed point of an operator as long as it satisfies certain properties. So look, what are we doing there? We're trying to get the greatest fixed point type L that contains unit. That's going to stand for nil, and it contains products of T's and L's. So that's going to be our cons operator. And if you think of it, first of all, what's that union sign there? That's just a bare union of the two types. No little markers saying which one it is. You just union them together, and I'll show you how that's created inside of NUPERL. But anyway, just intuitively, this is the type that contains unit, the elements of unit, namely this one particular star or axiom we call it. That's there. That'll take the place of nil, and then it's got all the pairs of a T and a member of this type, and it's the greatest fixed point, so it includes things that go pair, all the way down forever. So it includes streams. This colist is like the type of either streams or finite lists, because the nil is there. And so if you think of it, that's really what lists in Lisp are. They're just con cells or a particular, nil. So let me show you how. First, I'll just pop this definition of union up. Well, but I think in Lisp you can create circular lists, so they would, in some sense, I don't think Lisp would force you to not have a circular list. So I think in some sense you could create a stream in Lisp using this data type. I think. I'm not a Lisp programmer, but I don't think Lisp, Lisp is untyped, so you can overwrite things. I think you can create circular structures in Lisp that would sort of still be this.
Sure, but you never create an actual infinite structure, right?
Not it would. Yeah, well, and still, here we don't sort of actually create an infinite structure. Because we use lazy evaluation, so you always have like a finite term which will evaluate as far as you want. I don't know.
So for example,
Yeah.
circular one, but it's pretty that one was always increasing.
Yeah, so I think it would be hard. Yeah.
people have all natural numbers.
Yeah, but I mean, I think in Lisp, well, with closures and everything, you might be able to create a thing which would.
But that wouldn't be a list anymore.
Yeah, maybe not. I don't know. Well, anyway, I'm just saying this is pretty similar to the concept of a list in Lisp. And anyway, it's okay. So here's the union of two types, A union B. Well, that's just a special case of the concept of a union of a family of types, but just indexed by Boolean. So what's the concept of the union of a family of types? So this is kind of a cool thing. So we're getting down to a primitive type here, but anyway. So some while back we added in this concept of a union. We have intersections of families of types. Why not unions of families of types? Turns out unions of families of types is more complicated than intersection, because in intersection you're just saying the members are the things that are in all of them. The equality holds between two things if it holds in all of them. In union, you say the things that are in the union are the things that are in one of them, but when are two things equal in a union? That gets complicated because it doesn't mean they have to be equal in one of the components, because if you have the union, if I'm unioning two types together, and this is equal to this over here in this type, and this one's equal to this over in this type, then this one has to be equal to this one in the union. So the union is really, if you think of the types as partial equivalence relations on terms, the union is really, you union together all those partial equivalence relations, and then you take the transitive closure of all of that. So it's more complicated type to deal with. Like what are going to be the rules for reasoning about that type? It's kind of complicated, it turns out. So we used to have it as a primitive type, and there were a bunch of rules about it in order to reason about equality in a union, and they weren't actually very good. I mean, it was hard to reason about union. So then Bob's students, Alexei Kopylov and Alexei Nogin, after they had left Cornell and gone to Hughes Research or somewhere, I forget, they were still working on their version of New Perl, and they came up with this type, the image type. It's a very fundamental concept, and it's pretty straightforward. You say, well, here's a type T, and here's a function f that applies to members of T. Why can't I just form the type of all things that are, another type which is just, whose elements are just all the things that are of the form f of x for x in T. It's just the image, just like in set theory, you would take the image of a set under a function. Why shouldn't that be a type? Well, you have to define the members. The members are just the things that are f of something in T. And then the equality just says an f of x is equal to an f of y if the x was equal to the y in the original term, in the original type. So it's actually a pretty simple concept, the image of a type under a function. To be well formed, in general, there's a restriction. The function that you're using to make the image, it has to, if it would depend on some other parameters in a non-trivial way, then it would turn out that this wouldn't necessarily be a well-formed concept. But if that function is in base, the function itself is only defined by squiggle equality, then it works. So you can take the image of any type under any function that's in base, that doesn't have any any parameters from some other type with a non-trivial equality. Anyway, so if we take the dependent, we call the dependent product type, that's the sigma type. It's the set of all pairs of an A and a B, and we just apply the pi2, the projection onto the second component, then what do we have? We have all those things that was where you had an A, all those, so we have all the types. So we've got, for every A, we have a type B of A, and so we've got, well, we want to get the union of all of these B of A's, but we take, all the pairs of an A and a B, so the B will be a member of B of A, and we just apply the pi 2, so we have all the B's. So the members of, anything that was in one of these B of A's was part of a pair, A, B of A, and then we just project off the second component. So that's the way, using the image type, we can get the union of a family of types. And the advantage of that is somehow, again, this is the power of generalization somehow. The rules we had for the union type were messy and hard to work with, and somehow there's fewer rules about image type, and this definition, in terms of image type, now all the properties we wanted to prove about union type are easier to prove somehow. So there's like somehow the power of generalization, and this is like, we're all reading up on Blavatsky's program and how he's inspired by Grothendieck, and Grothendieck was always doing that throughout his career, saying something or other, keep generalizing, and if you generalize enough, all the proofs will become trivial. That was his motto, So, I don't know. These proofs are not trivial, but still, somehow this concept of keep taking concepts and see if you can come up with some even more basic concept from which you can define that. Sometimes it has elegance, but sometimes it also makes the proofs easier. So anyway, so there we have the definition of union. So now we got to go look at our definition of co-recursive type. So we know what we're doing. We're trying to get the fixed point of this union. And so now let's look at the definition of co-rec. Okay. So here's the idea. This type top. So here's the type top. I could pop up the definition, but the type top is got this very, very cryptic definition. But if you think about it, so remember we have the intersection of a family of types. So now we're taking the intersection over the void type, and it doesn't really matter what we put over here because since there's nothing in void. So for T to be in here, it has to be in this type over here for every member of void. Okay, all right, I'll start over again here. So, top is intersection X in void of, doesn't really matter, but we use void just because it looks cool. You think, this is such a puzzling type, you think, but still. Now, what does it mean? A term T1 is in here just if T1 is in void. So this is like, void of X, but it doesn't depend on X. For all X in void. That's vacuously true. There are no members of void, so to say it has to be in void of X for X in void is saying nothing. So that says every term is in top because there's no constraints. You have to be in this type for every member of void, but there are no members of void. So top contains all the terms, and then when are two terms equal in top? T1 is equal to T2 in top if, again, for all X in void, T1 would be equal to T2 in void. But since there are no members of void, that's also vacuously true. So not only is every term in top, but every two terms are equal in top. So top is really the same thing as all the terms base quotiented by the always true relation. So it's basically saying, so that should say base. It's all of our terms, but now the equality has been made trivial. So top is a type that has all the terms, but in some sense it only has one. It's got one equivalence class that contains all the terms. So that means that every type is a subtype of top, because to be a subtype means everything in here has to be in here. That's satisfied. And two things that are equal here have to be equal here. But since everything's equal to top, so top is really the top of the hierarchy of types under inclusion, under subtype. So it really is the top type. So now, if f is a monotone function, so if a is a subtype of b, then f of a is a subtype of f of b, then f of top is going to be a subtype of top, because everything's a subtype of top. And then f of top is going to be a subtype of f of top by monotonicity, and then f of f of top is going to be a subtype, and so on. So as you apply f from top, you're just possibly going down. You're getting a chain of types. Here's top as a big, and here's f of top, and f of top, and so on. And if you intersect all of those, you get a type. And now if f is monotone and satisfies a certain property that I called continuity, but I've been informed other people say preserves omega limits, then this theorem is true. The co-recursive type is a fixed point of f extensionally. So this triple bar just means subtype in both directions. So co-recursive type is a fixed point, and you can show it's actually the greatest fixed point, provided you have this continuous monotone thing, and I'll show you what that is. It's just monotone and continuous. So monotone is what you expect. If A is a subtype of B, then f of A is a subtype of f of B. But continuous is, I probably misnamed, but this is what, so it's a bit, so it's saying if you have a family of types and you apply f to all of them and intersect that, you get the same thing as intersecting all of the family of types and then applying f. I mean, you get a subtype. So you just have to read that. That just turns out to be exactly what's necessary to get that thing to reach a fixed point after only omega steps. In general, I guess, for an arbitrary monotone function, even to get the greatest fixed point, you might have to iterate farther. You might have to iterate all the f of n's, intersect all of that, and then iterate some more, and eventually reach a fixed point. But if it satisfies this property, then you've reached the fixed point after the first omega steps. And that turns out to be true of almost all the type constructors we have. So we can almost always get a co-recursive type by this construction. And in particular for that list thing, it does. So now, I'm going to stop before I reach 10:20 because I think questions will be more fun than me doing more things. But I just want to show you one last thing. Because so now we've seen all the ingredients of this definition of the list except for what that co-list thing is, but co-length. But co-length is really just the same definition as you would make for length on list. So you just write down. So in Nuperl, when you want to make a recursive definition, and like in Coq, you would say fixed point or something, and then write the thing you want. In Nuperl, you just make you say add recursive definition. It gives you a little template. You write down your recursive definition, and then it creates this fixed point version of it, and it creates some lemmas for working with it. But anyway, so essentially, co-length is just what you would write for length. So remember, the list the type we're talking about is built from unit and pairs. So we have to have a way to decide, are we looking at unit or are we looking at a pair? And so in Nuperal we have these canonical form tests. So you can you can try to test whether a term has some particular canonical form. The canonical form test says, compute the term. If you get a value, then if it's that canonical form, return the first case, and otherwise return the second case. So here we can just say, if L is axiom, which is going to stand for nil, then the length is 0, and if it's not, then we know that it must be a pair, and so do the spread of the pair and get the co-length of the tail, and then add 1. So if this co-list goes on forever, then this length computation will go on forever. It'll go 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, and it'll end up diverging. But if the list is finite, it'll go 1 plus 1 plus 1 plus 1 plus 1, and then it'll stop somewhere, and then the length will converge. So all we have to do, so that means that this is a sensible definition for the lists, because the idea is somehow the co-recursive type is in a way easier to describe. I mean, that greatest fixed point is pretty straightforward. You just iterate the thing and take the intersection, and you have your co-thing. To describe the recursive thing, you have to say it's the well-founded part of that. And so this idea of just making basically a size function on the co-thing and then just saying, well, wherever the size function eventually terminates, that's the well-founded part. That doesn't work for W types, but it works for normal sort of finite algebraic data types. So the only thing I want to show you real quickly is how do I prove that this is even a well-formed definition. I have to prove that co-length, whether co-length of L has a value, is a well-formed expression. I have to show that. So that's where we use the partial types. So I'm just going to show you real quickly how we prove that co-length is well-formed. Okay, so here's my well-formedness lemma for co-length. It says, given any type and given L in co-list T, then I want to show that co-length is a well-formed expression of type partial nat. So partial nat is the type that we used to write with the bar. It either converges to a natural number or it diverges. So first of all, one more digression. Let's look at the definition of partial. So, So the idea of partial is it's going to contain all the things in the type T and the diverging things. And what's the equality? It should be the case that two things are equal in there if they either both have a value, in which case they are equal in T, or they both diverge. And so we can actually define that using the quotient type, which Bob mentioned. So the base partial type are just all those things in base such that if they converge, they're in T. And remember, in my first talk I said whether something's in T is always well-formed as long as the thing is in base. So that's a well-formed expression. And if it's in base, it's also well-formed since squiggle equality preserves, two things that are squiggle equal either have to both diverge or both converge. So having a value is a well-formed proposition about things in base, and so is whether it's in T. So this is a well-formed type. Those are the base elements that I want to put into my partial type, and then the equivalence relation is that I want to say they're equivalent, x and y are equivalent if one converges, then so does the other one. So that says U if and only if. That's a uniform version of if and only if that's defined using intersection. But anyway, essentially we just say one converges if and only if the other one does. And if one of them does converge, then they have to be equal in the type T. So this is again showing, so again, in the original version of the partial types, that was originally defined by Bob and your student Scott Smith really was the original one, and then it was elaborated greatly by Carl Crary in his thesis. So they worked out all the theory of how you reason about partial types and how you do something called fixed point induction using the partial types. And the interesting thing is this concept of fixed point induction isn't universally valid. There has to be this condition called admissibility. And anyway, it was turned into, Crary's thesis is very interesting, and he elaborates all this. But anyway, they originally defined this thing, meta-theoretically, and they put in all these rules, and Crary's thesis ends up having hundreds of rules for reasoning about this, so he could give an entire semantics for ML using that. But we're not using it in the depth that Crary is using it, so we don't need quite all of that. So by this definition in terms of quotient, it turns out we can capture most of the properties that he has without having many, many, many rules. So this turns out to work fine so far, So anyway, so that's the definition of partial. So now, I have to prove that co-length is a well-defined function from co-lists into partial nat. So I just unfold it, and now it's a fix of this thing, and I have to show that a fix is in a partial nat. Well, that's exactly what fixed point induction is about. When is fix of f a member of partial? Under certain admissibility conditions, fix of f is a member of partial provided the body of the fix is of the right type. So we have proved, using that quotient definition, I can't show you the full proof of this fixed point induction lemma, but I'll just show you what the lemma says, and then, so let me find that. Fixed point induction bottom. Let's see if I can find it here. Fixed point induction bottom, I think that's it. Okay, so we'll just stare at this, and then that'll be probably enough for... Okay, it says, okay, so we're trying to show so what I have to show is that fix point of a certain lambda something applied to L is in partial nat. So I have a fixed operator in a context. This is the context G of, the context is take this and apply it to this L. So this lemma here says in any context G which maps S's into partial E's, if I have a little g that maps S's to S's, then G of fixed G is going to be in partial E. So intuitively you think, well, why should that be? You think, well, the inner fix thing is either going to terminate at some point and give me an S, in which case G of S will have partial E, or the inner fix will run forever, and then it'll be bottom, and then G of bottom wouldn't necessarily be well formed, but here I'm assuming that bottom is a member of this type S. So in that case, then G of the fix would also be in partial E. Anyway, this turns out to be true provided S contains bottom, and we have these other two conditions. So this value type E is the thing I was talking about. E is a type that contains only values. And that's basically there to make the type of partial E a well-formed type. And then we have this other funny thing, mono of E. So fixed point induction is just not valid in general. And there's tricky counterexamples first. I think Scott Smith discovered the first examples, I think.
It went back to the LCS.
Yeah. So they all knew that. Yeah. So anyway, there are examples where this principle is just not right. And so you need some extra condition. So they came up with this notion called admissibility, which is rather complicated. Basically, admissibility just said, it's the proposition that fixed point induction is correct, kind of, and then they tried to characterize it in various ways. But at the end of Crary's thesis, he says, here's a concept called a type being a monotone type, which pretty much captures admissibility in all the easy cases. And so basically for us, that's the only one we ever need. So I'll show you what mono means. So a type is mono. So essentially what it says is, here's a type T. If I have one member A in this type T, and then I have this computational approximation relation to another member of type T, then in fact A and B are actually equal in the type. So in other words, a type is like integer. If you have an integer and an integer approximates something else, well then those integers are the same because they're already canonical. So like a type that would not be mono would be one that had, say, pairs of bottom and bottom, and then you could go up to like, one bottom, and then you could go up to 1, 1, something like that. If all of these were in the type, then there's this approximation, and unless they were all declared equal in the type, then that type would not satisfy the mono property. But for types that do, so the idea is type is monotone if you can't go up in the type by this approximation relation in a non-trivial way. So anyway, the natural numbers have that property because all the natural numbers are just compute to canonical forms. There's no non-trivial approximation going on in the natural numbers. So that satisfies that. So anyway, so that sounds, if you sort all that out, you might say that that's the most complicated definition of the list type you've ever seen. But in fact, this is pieced together, from really basic things. Basic proposition about computation. This basic construction of just iterating a function and intersecting. That's really so. These you say, well, what about Cox inductive construction? That's pretty basic and really understandable. And I would agree, but I'm saying this construction here. If you look at what induction principles I needed induction on the natural numbers in order to prove that my co-recursive type exists, and I needed induction again on the natural numbers in the concept of fixed point induction is just talking about iterating something until it reaches a value, and then something reaches a value in finitely many steps, or else it diverges. So the only induction used in this whole construction is induction on the natural numbers, which is very fundamental. The inductive construction in general is a way more powerful induction principle than that. So you could say using the inductive construction to build lists is using a sledgehammer to build something that's really easy to build. I mean, so it's just a matter of taste. But when we hit on this, we realized, we did this because the version of the recursive type we were using was even more powerful than the Cox inductive construction. So it was way overkill for building the list type. And at the moment, we don't have a soundness proof for it. So we could have, and we do have a soundness proof for W types. So we could just use W types for lists, and that would be perfectly fine. So there's no need to do it this way, but it's just I don't know. It's just we like the fact that all these pieces fit together in this way. And actually, once you've defined lists and you've defined using this definition, you've defined the iterator for lists, then everything else about the theory of lists goes through just as it did when list was a primitive. So nobody, this is like an implementation of lists using what we have, which doesn't really matter once you get going. I'm going to stop and we'll have like 5 minutes for questions and stuff. So I guess that's it for me. Yeah. Properties of bottom. Yeah, I'll show you the basic. Yeah, so Peter was asking me about, how, to what extent can we reason about general recursive functions in new Perl. So here's basically the principles we have. Bottom does not have a value. And then we have this property. Fix of G in some context. So if you have a fixed point in some context, if that has a value, then there exists an n for which G of G to the n applied to bottom has a value. So this is saying, in any context, if you're iterating and you managed to reach a value, then that must have happened at some finite, after finitely many iterations. So this is called the compactness rule, and that's proved in the meta theory based on the properties of computation that we have. And then there's one other one that says it says that if, again, I think it's in any context, G of fix of G is less than or equal to T, G of fix of G is less than or equal to T provided for all n, G of fix of G to the n of bottom is less than or equal to T. So this one's called the least upper bound rule. So it's just saying, so basically, all you need to do, the only kind of recursion we have in new Perl is generated by this fix operator. All we have is, we build up all the other recursion operators just by using general recursion. So basically, new Perl doesn't have any primitive recursive things built in. We build the primitive recursive things from the general recursive thing, and then we get all of their properties just basically from these two laws of reasoning about iteration. So basically, bottom could be just defined as fix of the identity function, and then you would deduce that it must diverge using this, except that these rules mention bottom. So to get started, we have to have one sort of primitive diverging thing, because otherwise, I don't know. So anyway, that's basically, so that it's pretty nice that, so many facts about general recursive functions just follow from those two things. So that's why we think, those two least upper bound and compactness properties, those are like the kinds of things that people who, study domain theory, reason about. They reason about them in, very abstract settings, and, so this is like a very concrete version of domain theory here. But we're calling it like constructive domain theory, but we're not sure to what extent it covers like all the things that people who use domain theory can do. But as far as the applications of domain theory to proving various facts about recursive functions, it seems to work. So, yeah, okay. That's another question. Yeah.
Define lists with a standard list fixed point construction, starting from void and taking a union.
Yeah. So so the thing is, you could do the same thing. You could start with void and do f to the n of void, and then take the union of that family. So, as I said, reasoning about the union type is more complicated than you'd think. They'd just be totally dual, but intersection is very easy to reason about, because something is true of an intersection if it's just true of all the members, including equality. Some things are equal in an intersection if they're equal in all the members of the intersection. But to be equal in the union is to be in the transitive closure of the equality of all of them. So somehow this union thing adds complexity. So I was able to construct lists this way, but I had to prove a stronger property of this F. It's like you need something like I had to prove that, so I'm trying to prove just for any monotone function F, but in this case, I had to say F has this property that I called, it has constructors. Somehow like the F has to be built from things like pair and stuff for which you can destruct. It has to have a set of constructors for which there exist destructors. So it became a more complicated condition, but it does. You can prove that for the Fs that you would normally use for algebraic data types, you can do this construction and then actually get the same thing as the other thing, but it kind of messier. So, yeah.
So when we were looking at recursive functions, Bob mentioned that if you had the plus function, something is agreeable in context that it would be defined asymmetrically. Recursive on one argument but not the other.
Yeah.
And you mentioned that in Newfer, this problem didn't really exist, and that if you had plus 0 something, it would reduce just as well as plus something 0.
Yeah.
Can you give an intuition to why?
Well, so you're saying so in Coq, 0 plus n is equal to n plus 0, but only propositionally equal, not definitionally equal. Isn't that right? Yeah. So that means in Coq you can't just replace this by this in sort of like any context without doing some sort of, I don't know. But yeah, but
to prove this in Coq, you need to do induction on it.
Yeah.
Because one side computes directly to n, but the other side does not reduce because n is not.
Yeah. So anyway, in numeral, these are squiggle equal, and that's just a fact about the integers that basically. So how do we? I'm trying to remember if that's a primitive fact or a derived fact, but okay. No, it's certain at least. So the integers have the property. So again, suppose n is equal to m in the integers. Then I'm going to, just as a typed equality here, I'm going to then claim that n is squiggle equal to m. Because the definition is, for any canonical form that this computes to, and in the integers, there's only, the integers are canonical forms. Yeah, so that's another thing. So maybe that's the difference. In Coq, the canonical forms for even in Coq it should work. I mean, if they had the definition of squiggle equality, it would still work because, in Nuperal, the canonical forms for the integers are just, integer, and then there's 5 or something. We don't build them up from successor, 0. But still, even if we did, it would be successor, successor 0 or whatever. Anyway, so if this computes to a canonical form and they're equal in int, then this one would have to compute to the same canonical form, and then so it would be the case that any two things that are equal in int are actually squiggle equal, and then using the fact that n, you can prove that n plus 0 is equal to 0 plus n using induction or however.
So that proof would require induction as well?
Yeah, it could be done by induction, but you could state it by induction. As I said, in Nuperal, we just bring the integers in from the outside as a primitive constant, and we just have the ring axioms for them. So this is actually just a rule in Nuperal, that commutativity in general. But you could go back and reprove it, by induction.
Because once I proved it in Coq, I also reread that it can do that issue.
Oh, you're saying just how to prove it is the issue.
I mean, the problem in Coq is that proving it is disagreeable because there's a symmetry in
Yeah.
the definition of plus. So.
Oh, I see. Well, so you can say, well, Nuperal just cheated by just taking a shortcut and just putting in the ring axioms for the integers as rules. But I think there are some cases. But remember, people are telling me, like in Coq, if you make like this vector type that's parameterized by a number, then you come to vector of 0 plus n and vector of n plus 0, are different, intentionally different types. So you can't, when
Rewrite
you can, I mean, you know, but anyway, there's various issues where in Coq you might need to kind of use setoid rewrite or something, you know, I don't know. But anyway, this squiggle thing is very helpful in Nuperl to just say when things are squiggle equal, you can just replace one by the other in any context and no issues of well-formedness or anything arise. So I think we're supposed to stop, but if anyone has one more question, yeah.
So just with regard to the last question,
Yeah.
I think that like one thing that might clarify a little bit is just so in Nucro, like yes, you still just as in Coq, in order to prove that you have to go by induction on the number, or in general, it will be a proof. It's not just going to hold definition. But the difference is that in Coq, you're going to end up in a place where in the actual term, you're going to have some kind of a rewrite, like a subs or an application of the J eliminator. Whereas in Nucro, that reasoning goes in the derivation of a judgment, not in the actual term.
That might be a helpful explanation for some people. Yeah. Right. Anyway, I think, you know, Howe's relation is actually an amazing thing. So if you know, whether or not you're going to work with a system that sort of has it, you know, natively, you know, you should just study up on it. You know, because it's a very useful. I think, you know, various people who do program semantics and other things, they say we're now going to define a contextual equivalence relation using Howe's trick. That's like a phrase that's used. So you should study up on what Howe's trick is. The Howe's trick part, it turns out, you know, that definition I'm giving you that says if this computes to a canonical form, then that's how it's defined for closed terms. But in order to extend it to the whole thing, you have to extend the definition of squiggle equality to open terms, and that's where Howe's trick comes in. He had a clever way of doing that, and it was tricky. But yeah, it's a very, very useful concept in any kind of semantics of computation systems. So, and then, you know, you can reflect it into the logic the way we did in Nuperl, and it's very, very useful. But you know, it's still a useful thing to know about. I think so. Shouldn't we stop now and have a break? I think. All right.